Today I'll be talking about acids and bases and the questions I've encountered during my study of them. This is Conquering Chemistry with Cho, and today I just wanted to talk a bit about chemistry instead of math. So, a definition of an acid. Um, I thought that there were three different types of acids or definitions of acids, and the first one was Arrhenius acids, Bronsted-Lewis acids, and Lewis acids. So an acid can be defined as a chemical substance that donates a hydrogen ion or proton or can form covalent bonds for an electron pair. Chemical substances that can donate a hydrogen ion in water are called Arrhenius acids. Those that can donate protons are called Bronsted-Lewis acids, and those that accept an electron pair from other substances are called Lewis acids. Now this might seem hard at first, but all we need to know is how many ways an acid can be defined and the similarities between their definitions. I talked before about how some acids are defined by their ability to form hydrogen ions in water. Hydrogen ions are represented as H+, and they are basically a hydrogen atom without an electron, and that would cause a positive charge on them. And what Arrhenius acids are there are substances that form hydrogen ions when in water. That's what they define the acids, Arrhenius acids as. Now, increasing the concentration of hydrogen ions in water, that's a very specific definition. And some other scientists didn't approve completely with that, so they made a wider definition, which is a proton donor. So in Arrhenius acids, you have to be in water, or the acid has to increase the concentration of H plus in water. But in Bronsted-Lewis acids, it can just get their acids are defined as substances that donate a proton to other molecules or substances. And there are Lewis acids who accept electron pairs and form covalent bonds with other substances. And finally, we need to understand that Arrhenius acids are the most specific definition of acids. Bronsted-Lewis acids are more general, and Lewis acids are the most general. Now, there are something called monoprotic acids, diprotic acids, and polyprotic acids. Monoprotic, mono is a prefix for one, which in this acid, a monoprotic acid is an acid that donates one proton or either creates one hydrogen ion when put in water. Now, diprotic acids, di is a prefix for two in Latin, and diprotic acids produce can donate two protons or can create two hydrogen ions when put in water. An example of a monoprotic acid is hydrochloric acid, and an example of diprotic acid is sulfuric acid. Now, sulfuric acid has the chemical structure of H2SO4, and the coefficient of H is 2, and when put in water, it dissociates into two H plus ions. Polyprotic acids are acids that donate into 3, 4, 5, um, dissociate into 3, 4, 5 hydrogen ions, or can donate 3, 4, 5 protons.
Now on to the next question. To answer this question, we first need to start by defining hydroxide concentration and pH. Concentration is how many molecules of a certain substance are in a solution. The units used in chemistry are mole divided by dm cubed. Hydroxide concentration represents how many hydroxide ions there are in a solution. pH is a value that ranges from 1 to 14 and represents the amount of hydroxide or hydrogen ions there are in the solution. Similarly, pOH represents the amount of hydroxide or hydrogen ions there are in the solution, but the numbers represent opposite things. For example, on a pH scale, one would be highly acidic, but in a pOH scale, one would be highly basic. There are two formulas that allow us to calculate the concentration of both hydroxide or hydrogen ion concentrations and show the relationship between the pH and pOH scale. The first one is negative log of the concentration of hydrogen ions in a solution equals the pH, and negative log of the concentration of hydroxide solutions equals pOH. The second one is pH plus pOH equals 14. Fun fact, P in mathematics is used to represent negative log of something. So it makes sense. The P of H is the negative log of H plus ions. When there are more H plus ions, we call the substance more acidic, but the pH level of the substance is closer to the lower end of the scale. Why is that, you may ask? The concentration of H plus or OH in a solution is always between 10 to the power of negative 1 mole dm cubed and 10 to the power of negative 14 dm cubed. 10 to the power of negative 1 is far greater than 10 to the power of negative 14, but when we put it into the equation, which has a logarithm in it, it becomes 1 instead of a higher number such as 14. To answer the question of how hydroxide concentration and pH of a substance are related, first of all, we need to understand that they are not directly related. From substituting pH for a negative log of the concentration of H plus in the equation pH plus POH equals 14, we can see that pH minus log of concentration of hydroxide ions equals 14. Log of OH minus equals negative pH plus 14, and 10 to the power of negative pH plus 14 equals concentration of OH ions, which is the concentration of hydroxide. This sums up the relationship that they have. 10 to the power of negative pH plus 14, it gives the hydroxide concentration. Hydroxide concentration can be used to find the POH first. From that, we can find the pH of a substance because pH and POH always add up to 14.
Autoionization is the process that pure water goes through, which dissociates several of the water molecules into hydrogen and hydroxide ions. The dissociation reaction of pure water at R2P, or room temperature and pressure, is represented as H2O equals H plus OH minus, and it is reversible. This means that the water can dissociate into the ions, but the ions can also get back as H2O. In this reaction, the concentration of H plus and OH minus are always the same. This is because these two ions are product of the reaction. When 1 mole of water dissociates, it always dissociates into 1 mole of H plus and OH ions each. Even if the forward reaction is preferred, which means that more H plus and OH ions will be made, the concentration of those will always remain the same because of the mole ratios. It is crucial to remember that concentration does not have to do with the mass of the substance, but the number of moles of it. The pH scale shows the amount of H plus and OH minus in a solution, and even though water will be neutral at any point because of the fact that the concentrations of H plus and OH ions are the same, since the number of these ions are increasing, the pH might drop. So what this means is that even though the temperature or the pressure might affect the reaction by creating more H plus and OH minus ions, water will always be neutral at any point because the concentration of these ions are always the same. However, because the number of these ions are increasing, the pH might drop. The reversible reaction is affected by temperature and pressure applied to the pure water. If there is a higher temperature of the water, more water molecules will dissociate, creating more ions. If there is higher pressure, then there is a higher chance that water molecules will break by bumping into each other. It is true that a strong acid has a large acid dissociation constant. A strong acid is defined as an acid that dissociates in water to produce a lot of hydrogen ions or a substance that can donate a lot of protons. An acid dissociation constant shows how strong an acid is. If there is a larger acid dissociation constant, it shows that the acid is strong and vice versa. In general equation of acid dissociation, HA equals H plus A minus, the acid dissociation constant can be found by multiplying the concentration of H plus and A minus divided by the concentration of HA. If there is a lot of H plus ions that are generated from the dissociation from an acid, it means that the concentration of H plus ions and A minus ions will increase while the concentration of HA will decrease. The concentration of H plus and A minus will be the same in a solution if the mole ratio is 1 to 1. Looking back, a strong acid produces a lot of hydrogen ions in a solution. If many hydrogen ions are produced, the concentration of them in the solution will increase, which overall increases the acid dissociation constant, making the above statement true.